functions. Our objective today is to determine whether a relation is a function. Okay, think of a function as a machine. You put stuff into a machine, in this case we're putting 2 in, and you get an output, you get the final product. So when you plug in 2, the output is 10. So what could cause 2 to be 10? What are some things that you could do to 2 to get to be 10? Hopefully you're thinking multiply by 5 or adding 8. Those are the two, pretty much the two generic options. Your input is also known as your x or your domain. Your output is known as your y or your range. So let's take that same function, that same machine, and this time we're going to plug in 3. And what happens when we plug in 3? We get an output of 15, which pretty much narrows it down to our function is multiplying the input by 5. And if we do another one, this time we're going to plug in 4, and we'll get 20. And we could keep going forever, but we'll do one more here. We'll do 7. If we plug in 7, we get 35. So our function here is y is equal to 5x. And I want to remind you that x is our domain, y is the range. You could also set this up as a t-table, which is what we're going to be mainly dealing with today. So if we plug in 2, we get 10, 3 times 5 is 15, 4 times 5 is 20, 5 times 5 is 25, and 6 times 5 is 30, and 5, wow, just not doing well. 7 times 5 is 35. All right, some definitions here. A relation is any set of ordered pairs. So a set of an x and a y coordinate. We talked about those in section 1-10. A function is a special type of relation. So it's a type of relation where there's exactly one output for every input, which means for every x there's exactly one y. So here's our t-table, and we have our x and our y values, our domains, our ranges, our inputs, our outputs. And if you look through these, you'll see that you got -6, 4, -4, 0, -2, -5, 0, -5. And the way I've kind of explained this is that think of the x value, the domain, as a phone number. Now, when you have a phone number, it reaches one person. So, -6, if you dial -6, you're going to get 4 for it's going to pick up the phone. Now, some of you might be saying, well, what about -2 and 0? How would it be possible if I dial -2 to get -5, or if I dial 0 to get -5? Well, how many people have a cell phone and a house phone? Lots of people. And you could call your friend and reach them on their cell phone, or maybe call them at home and reach them on their house phone, or maybe they have a job and they work somewhere that you could call them at their office phone. So it's okay to have a y value, have y values to be the same. It's not okay for x values to be the same, and we'll talk about that more in just a moment. Another way of setting this up is with kind of these ovals. I'm not really sure what they're called. I should know, but I forgot. And so we put all the x values and we put all the y values, and we don't repeat them. And you can say, okay, -6 got you 4. -4 is 0. -2 is -5. 0 is also -5. Again, those are two phone numbers calling one person, and that's allowed. 2 is 7, and 4 is 4. So this would be a function. Here's another example. Now in this case, you'll notice that the x values repeat. So what this is saying is if you call one phone number, sometimes you'll get 6, sometimes you'll get 7. Well, that's not going to work for a phone, because if sometimes you call and you get your best friend on the phone, and other times you call and you get Mr. Gore on the phone, you're not going to be happy. You're not going to want to call your best friend because you're too afraid of getting me on the phone and you don't want to talk to me. And I understand that. I'm okay with that. So this is not a function. It's not a functioning phone number or not a function because you get different values for the same x. You can only have one value for each x. It doesn't change. So here's a couple of examples. We're going to do 3 examples and let's see if you can figure out which one's a function and which not. So take a look at this, pause the video if you need to, and decide whether or not this is a function. Okay, so my hint to you, my basic dirty trick is look at the x values, look at that left side. Do you see any values that repeat? Nope, there's no repeating x values here. So then this is a function. If you see a repeating x, 99% of the time it's not a function. So let's look here. Decide whether or not this is a function. Pause the video, write it down, and make your decision. Well, there's no x values that repeat. I know that you see this and you say, well, there's the y values repeat. That's okay. Remember, that's the house phone and the cell phone. And that's allowed. So this is a function. Now look at this one and decide if this is a function. Pause the video if you need to. Okay, this is, if you look at the x values, do you see any x values that repeat? Right here and right here. Therefore, since you have repeating x values, that means you've got one number going to 2 different people. This is not a function. Next, here we have 4 sets of ordered pairs. Decide whether or not this is a function. So you're going to look at your x values. Remember, x values are the first digit of each ordered pair. So if you look here, our x values are -1, 0, 1, and 2. No x values repeat, so this is a function. Take a look at these and decide, write them down and decide if this is a function. Okay, so if you look, you've got 4s repeating in the first order, or sorry, the second order pair and the last order pair. So this is not a function. Okay, copy down this line onto your graph, and we're going to do what's called the vertical line test. So if you take your pencil or pen, and you're going to drag it across, and as you drag it across that red line, do you see something that looks like it's, or does it touch more than one point at the same time is what I'm trying to say here. So here's my line. Watch my line as I go across. Does it touch more than one point at the same time? And the answer is no. It touches only one point at each time. The x values are your phone numbers. The y values are the people, and you're only ever calling one person on this line. So this is a function. Here's another line. Go ahead and draw it and decide, do you think this is a function or not? Watch my blue line. Did it touch the line in 2 parts at the exact same time? And the answer is no. So this is also a function. Here's my next line. I drag my vertical line across, and right there, is it touching more than one part? It's touching the whole thing. So what this is basically saying is you've got one x value, one phone number, and when you call it, you could reach anybody in the entire world. You don't know who you're going to get. And that's not a functioning phone, or so it's not a function. Draw this and decide, is this a function? This is what's called a parabola. It actually has its own special name. So as I slowly drag it across, I'm only touching one part at a time. So that's also a function. Similar, but kind of twisted around. Is this going to be a function? As I go across, Look, I'm touching two parts at the same time. That means it's not a function. And put some dots on your paper that looks something like this. And let's drag our line across. And as we do so, we're only touching one part at a time. So this is a function. Next. Is this a function? Nope. You can see right there it's touching 2 points at the exact same time. And is a circle a function? No, that one should hopefully be kind of easy. We're touching 2 points right there, so it's not a function. Okay.
Behold, milk chocolate. But where did it come from? Meet Daniel Peter, born in Switzerland in 1836. Daniel's father was a butcher, but Daniel didn't want to carry on the family business. Daniel also didn't have the best of luck. He originally went into the candle-making business, but the introduction of affordable kerosene lamps rendered his business obsolete. But Daniel was a determined young man, and once he married into the chocolate-making Kaler family, he focused his energy on improving chocolate. At the time, he manufactured chocolate in a dark tablet form, and it was used to make drinks, not to be eaten in solid form. Daniel wasn't the first person to attempt to improve chocolate's naturally bitter flavor, but he certainly was tenacious. For years, Daniel tried to add milk and chocolate together, but he didn't have any luck. At least not until he had a little help from another inventor, his neighbor, Henry Nestle. The secret? Condensed milk. Here's how it works. Regular uncondensed milk has a high water content, which means it can't combine well with cocoa paste, and any chocolate made from the combination turns rancid in a short amount of time. Yet by combining condensed milk with cocoa and a bit of sugar, Daniel managed to create a smoother, cheaper chocolate. This was especially true in Switzerland at the time. They had a lot of cows, but chocolate and sugar had to be imported. After 8 years of experimentation, Daniel hit on the stuff of genius. He partnered with Nestle, and the rest is history. So, how genius is this inventor? On the American Dream scale, he gets a 5. Talk about commitment. Daniel Peter went from a failed candle maker to the founder of the milk chocolate industry. On the benefit to humanity scale, he gets a 2. Chocolate is delicious, and studies have shown that it has some health benefits when consumed in moderation, but you can't live on chocolate alone. On the ripple effect scale, he gets a 5. Milk chocolate has spread across the world, and it's safe to say it will remain one of humanity's favorite sweets for centuries to come. For more stuff of genius, check out howstuffworks.com.
Let us know what you think.